All right. So we have finished planarity module 2, and today we are moving on to module 3, flows, cuts, and disjoint paths. Before we go on, are there any unresolved issues from planarity connectivity that you would like to discuss? We can take a few minutes to discuss whatever unresolved issues there are from previous modules. You can also ask any clarifications on assignment 1. So if you think that there is something which is not clear or there is some ambiguity in any question, then this is also a good time to ask such questions.
Sir,
Yeah,
I have a doubt on the algorithm we wrote for
yeah.
planarity testing. Can I ask it now or in the
You can
end of the
ask
class?
now. Let's see
Okay.
how.
Could you go on
Yeah,
to the algorithm?
yeah. So the one we wrote in the lectures.
Yeah, sir.
Okay.
Could you explain what is recursion here? Like, where are we using recursion? Like, I see only iterating here. Like, we would be checking whether C union BI is planar for every I, for
Right.
every bridge. Like,
Right.
where is recursion coming here?
But C union BI is
Hmm.
it could be as big a two connected graph as possible, right? So when you call this, basically what I'm saying is you call the same algorithm for the graph C union BI. This graph could again be very big, so it could again make more calls. So in that sense, this is a recursion. So what I really mean is call the same algorithm on C union BI. And that could be a pretty big graph.
Oh, okay, like basically you're saying that for every C union BI, like you should call from step -1, like say
Yeah, yeah,
those things as well.
right. That's right. I mean,
Okay,
if you want, you can call from step 0, but yeah, you could call from step -1. It's
hmm.
fine.
Okay, okay,
Yeah.
that answers my question.
Okay.
Thanks.
Thanks. Any other questions? Any clarifications
Uh,
required on this? Yeah,
uh,
Shafali, go ahead.
in this algorithm,
Yeah.
the part where we are checking if it is bipartite or not, uh,
Yeah.
there also we are recursively checking, right?
Not quite. We are not checking recursively here because the
Okay.
thing is, once the recursion calls have all returned, right? So for each bridge, you know that the graph C union that bridge is planar. Once you get that
Hmm.
information, then you only want to check whether the bridge overlap graph is bipartite. So at this point, you just
Okay,
construct the
okay.
bridge overlap graph in that particular iteration, in that particular call, and you check if that bipartite graph is sorry, if you check if the bridge overlap graph is bipartite or not. So there is no recursion here.
Okay.
Yeah.
Right, right. And there I got a confusion
Okay.
in the last lecture actually.
Okay.
Yeah.
Yeah, so I would strongly recommend trying the algorithm on some big enough graphs on your own. Maybe take a dense graph, I don't know, something like okay, if you take it too dense, then try the algorithm without the -1 step, right? The -1 step is only to get order m to be order n. So what you can do is you can start running the algorithm from step 0, and you can take some graph like k7 if you like, for example. Of course, you know that k7 is non-planar, but the point is to see the recursive algorithm in some number of steps, right? Because the example we did in the lecture, I think it only stops in one recursion level or two recursion levels. Okay. Any other questions?
Sure. So you had earlier there was a sort of doubt or discussion, long discussion about how K4, why should one of the points lie within the interior of the rest of the three?
Uh-huh. Right.
And you had given proof the next day and sort of trying to convince the rest of us uh, using some kind of a lemma. But that wasn't using Fary's theorem. I found a neat way to do that using Fary's theorem.
Okay.
So if you have,
Mhm.
so we can convince ourselves that triangle is the only way to get a K3, right?
Sorry, what is the only way to get a K3?
A triangle, three lines.
Yeah, closed curve.
But if you're using Fary's theorem, you
Oh,
can
you're
say
using Fary's theorem. Okay, sorry. Yes. Yes. So if you use Fary's theorem, then it is going to be a triangle.
correct. So now assume this is on the coordinate plane, and you can place the 3 points at any position, but just make sure that it's a you can form a triangle.
Yeah.
Now extend all the lines on the sides,
Okay. I
so you can
see. You mean you want me to go this way?
correct. You can
Okay.
extend all three, and now we notice that to place a fourth point to construct K4.
Mm.
So this is some sort of constructive algo. We can so you have 7 different regions over here,
Uh-huh.
interior of the triangle and 6 outer.
Yes.
Now, my claim is that you can only place a point uh, such that using 3 lines, you
Mm.
can join all three of these three of the triangle's vertices. If you can place it in the vertex projected exterior regions or or the interior of the triangle, you cannot place it in any of the other 3 regions.
Oh, I see. So you mean like here, I can place it here,
Correct, correct.
here,
So
here, and here.
correct.
Okay.
So if you can prove this, then interior of the triangle, we've already like you're placing the point in the interior, so it's already in the interior. We don't have to prove anything.
Yeah.
To prove that the point is there exists a point within the interior of a triangle in K4. If you place it in any of the other three,
Mm-hmm.
the the point whose projection or whatever those line segments are,
Yeah.
that will be the point which is inside the triangle. So for if you could place a in the first X you've drawn,
Okay.
you
Here.
just keep so place a point over there and
Okay.
you join all 3 vertices with line segments.
Like this.
Correct. So the point that you drew a line segment to the first time will lie
Mm.
within the triangle, right? So
Right.
right. So this happens for all the other 2 regions also on the exterior.
That's right. Right.
And now if you place a point in the white space region,
Mm-hmm.
it's quite obvious that a straight line segment joining the farther point has
Mm.
to cross intersection, uh, the edge in between the other 2 points.
Right. That's right.
So you cannot place a point over there. So this kind of proves why uh, there definitely exists one point
Mm-hmm. Mm-hmm.
outside. Uh, you know, you had regions in like back in that lecture, you had regions in C1, C2, C3, and you
Mm.
were trying to convince why point one was not in C1 was on the exterior of C1 or something like that.
Right. That's right.
Right. So
Yeah.
this proves that.
True. True. So in fact, if we use Fary's theorem, then even at the end of that lecture, there was a short discussion that yeah, using Fary's theorem, we could actually prove it. But then we were trying to avoid using Fary's theorem. So yeah, it is true that many arguments. Thanks for the argument. Many arguments in planarity may be simplified by using Fary's theorem. But since we are not proving Fari's theorem as well, we tried to avoid it in the lectures. And I would suggest doing the same on the assignment. So it's good to get these alternative arguments, but I would not suggest relying too much on Fari's theorem for the assignments. Right. So that's just, yeah. So that is true that using Fari's theorem, one can actually simplify many arguments, right? Because now you only deal with straight line segments and you don't have all sorts of weird, strange looking curves. Yes. So is everybody seeing why Fari's theorem can really simplify many arguments? Of course, we didn't prove it. And maybe I'll take a graph theory course next semester where I might prove it. I'm not sure. There are many other things I want to prove. Yeah. Any other questions, discussions regarding connectivity, planarity? Okay. So if not, then let us move on to module 3. Flows, cuts, and disjoint paths. So I want to do a quick survey to find out what everyone here has studied in their previous courses. How many of you have seen the max flow min cut theorem? Max flow min cut theorem. If you have not seen it, then please type no in the chat box. So everyone who has not seen the max flow min cut theorem, please type no in the chat box so that I have a clear understanding of where everyone is with regards to this theorem. So far only 3 people have responded no. 4. Only 4 people who have not seen the max flow min cut theorem. All of the other 15 or 14 people in the lecture have already seen the max flow min cut theorem.
Sir, most of us come from the design and analysis of algorithms course taught by Meghna ma'am, and she covered it in the class. So
I see. Okay. Right. Interesting. And did Meghna cover both? Did she also cover the more optimized version, like Dinnitz's version of max flow min cut?
No, sir.
Okay. I see. And did she cover some applications of max flow min cut theorem?
I think she did a few reductions. I'm not sure.
Bipartite matching. I see. Interesting. Probably also Menger's theorem. Did she cover Menger's theorem?
No, sir.
No. Okay. Good. All right. So we have at least 4 students who have not seen max flow min cut theorem. And it seems that people have also not seen Menger's theorem. So in that case, I will be taking a slightly different approach to motivate the topic so that it also gives a different perspective to those who have already seen the max flow min cut theorem. Right. So I will start with a different perspective, which is starting from connectivity, because by now you can tell that I am a fan of connectivity. Okay. So let's get back to the main discussion. Okay. So let us go back to the edge connectivity problem, right? So we say that a graph is k edge connected if whenever you remove k less than k edges, so k minus 1 or less than k minus 1, then the graph is still connected. For example, a graph is 5 edge connected if whenever you remove 4 or fewer edges, the graph is still going to be connected. In other words, to disconnect the graph, you need to remove at least 5 edges, right? And in one of the lectures, we discussed the decision problem. Decide whether a given graph is k edge connected or not, right? So if it is not k edge connected, that's very clear. You just show me a set of k minus 1 edges or fewer that disconnects the graph. So it is clearly in co-NP. And then we discussed that there is a polynomial time algorithm as well. And this implies that it is in NP, right? And what was the polynomial time algorithm we discussed? Well, we just said that choose for each subset f of the edge set such that f is less than equal to k minus 1. Check whether g minus f is connected. Okay. So if the graph has very few edges, if the graph has less than k minus 1 edges, then it's clear. So you can assume that the graph has at least k edges, and then you don't need to check for all subsets. You just check for subsets of size k minus 1. Okay. So you can always remove a subset of size k minus 1 and check whether the graph is connected or not after deleting these edges, right? And so how many such subsets? It is going to be m choose k minus 1. And each time you have to check whether the graph is connected. So that means that you have roughly order m algorithm for that, right? And this would be something like m to the power k minus 1 approximately times order m, right? And of course, then you can convert everything to n. That doesn't matter. So the point I want to make is that there is an exponential dependence on k. Right? Which is fine. If k is a constant, this is still a polynomial time algorithm. But it's kind of unpleasant, right? I mean, you don't want to have, ideally, you don't want to have an exponential dependence on k. Can we do better? Can we do better than this? Right? Can we, without depending on k, can we, for example, get a n to the power 5 or m to the power 5 algorithm to decide whether a graph is k connected or not, k edge connected or not? Right? Okay. And is everybody with me so far? Is it clear why we have an exponential dependence on k?
Yeah.
Okay. Good. So part of the problem is there is no, so far we have not discussed any sort of succinct certificate, NP certificate for the above decision problem. Right? How do you convince someone that a graph is k-edge connected? It's very easy to convince someone that a graph is not k-edge connected, right? But how do you convince someone sort of easily that a graph is actually k-edge connected? Any ideas? How would you convince someone? I don't want an algorithm, I want a certificate. How would you convince someone that a graph is k-edge connected? let's say k equal to 5. How do you convince someone that a graph is 5 edge connected?
Find the minimum set of edges that will disconnect the graph, and if the size of this minimum set is greater than
Right. So you're going through an algorithm. Let us convert that algorithm into a certificate. Okay, how do you convert this algorithm into a certificate? I'll give you a hint. For every subset of size 4 of edges, so we are looking at 5 edge connected. So for each subset of 4 edges, give me a structure in the graph that displays that the graph is connected after removing those 4 edges.
The 4 edges must bridge 2 individual components of the graph. So if you cut them, you get 2 disconnected components.
Right. So that would prove that the graph is not 5 edge connected. If you want to prove that the graph is 5 edge connected, then you don't want connected components. So you want a spanning tree in the resulting graph. Is that right? So
Yes.
what you could, right. So what you could do is for each subset f of the edge set such that cardinality of f is equal to k minus 1, provide a spanning tree of the graph G, delete the set F, right? If you give me a bunch of spanning trees of the graph, where for every set F, you delete that, and then you give me a spanning tree of the resulting graph, right? Which will also be a spanning tree of the original graph. If such spanning trees exist for all such subsets, then that would prove that the graph is k-edge connected. Does everybody agree? But this is also not succinct, right? This is an NP certificate. This is an NP certificate. But again, it has the same problem. It depends exponentially on k. You will have how many spanning trees? You will have m choose k minus 1 spanning trees. Right? So again, this depends exponentially on k. And that's the problem. What is stopping us from getting a good algorithm is we don't so far have a good NP certificate for checking whether a graph is k-edge connected. Okay. So, is there an easier way to convince someone that G is k-edge connected? That is the question I want to ask, right? Okay, so now let me give you a situation. Here is a situation. Supposing I give you a graph G and I tell you that between any two vertices, for any two vertices U and V, there exists K edge disjoint. Maybe I should be more precise. Pairwise edge disjoint paths UV paths. The path connects U and V. Supposing I tell you that this is true. I have given you a graph G. For any two vertices in this graph, there exists k pairwise edge disjoint UV paths. What do I mean by this? Let me give you an example. Actually, let me change the notation slightly to make it easier later. Okay, so I'm giving you two vertices S and T, and between the two vertices there exists k pairwise edge disjoint ST paths. What do I mean? So supposing this is your graph G, and this is S and this is T, then I'm going to set k to be equal to 3. So think of k as 3. Okay. What I will do is I will give you 3 paths like this: a red path, a blue path, and a green path. Okay. These are edge disjoint. For any two paths, P1 and P2, they don't share any edges. Okay, so this is P1, this is P2, and this is P3. Okay, and notice that the edge set of Pi, intersect edge set of Pj is empty for each ij in 1, 2, 3. Okay. So these are pairwise edge disjoint paths. Okay. And each path connects the two vertices S and T. Right. So that is what an ST path is. Okay. Supposing this is true, right? I've given you a graph G. For any two vertices, I'm telling you that there are k pairwise edge disjoint ST paths. Now my question is it possible that G is not k edge connected? Can you somehow remove k minus 1 edges from this graph and disconnect the graph? Is the question clear?
No, it's not possible.
It's not possible. Sorry, who was that?
That's me.
Okay,
Samuel.
Samuel, yeah. Anyone else? Is the question clear? What is the hypothesis and what we are asking? Let's see why this is not possible. So let's suppose it is possible. Okay, and I'm going to work with k equal to 3. Okay, so what you're saying is, in this case, you are able to remove two edges and disconnect the graph, right? So for example, you remove two edges and you disconnect the graph maybe like this, right? Or it could look like just two pieces. Can anybody tell me what is the problem? So let's look at this drawing. Can anyone tell me what is the problem? Anyone? Maybe not Samuel.
So when you disconnect the graph,
Yes.
there exist at least 2 points which are not connected anymore with the path.
Okay. So you want me to take a point here, let's say S, and a point here T.
Correct. So
Okay.
now we said that S and T to begin with are k have k disjoint paths between them. So, but we are only removing k minus one at most k minus one edges, and we're claiming to have disconnected the graph. But this is not possible because each of the path is disjoint. So you couldn't have removed lesser edges than k to have disconnected both S and T.
Exactly, right? The point is, thank you. So the point is that this edge in this drawing, in this particular drawing, this edge has to be used by every ST path. Any path joining S and T has to use this edge. So how can you have three edge disjoint paths joining S and T? Because each path has to use this particular edge. So you can't have disjoint paths, right? You can't even have two disjoint paths in this case. Of course, in this drawing, you can have two disjoint paths because one could use this edge and the other one could use this edge, right? But I told you that there were three paths joining any two vertices: edge disjoint, pairwise edge disjoint, right? So, right, so that's a problem. So in other words, whenever this condition is true, you cannot have that the graph is not k edge connected. Okay, I won't write down a formal proof. You should think about it in case the example was not clear enough. Okay. So the following is true proposition. If there exist k pairwise edge disjoint paths. So often when I'm speaking, I will forget to say pairwise, but I almost always mean pairwise when I say edge disjoint. Okay. So if there exists k pairwise edge disjoint ST paths between ST paths for all distinct S and T vertices of the graph, then G is K edge connected. Okay, so this is actually the easy direction of a theorem I'm about to state. Okay, so this is straightforward. You just make an argument from these drawings, right? But now what is interesting, and now recently I've learned the art of copy pasting on my lecture notes, so let me use that. Good. Can I move it? Okay, fine. Okay, so this direction is clear. What is really interesting is Menger's theorem. Menger's theorem is a theorem that has many different versions. So each time I say Menger's theorem, I will tell you which version it is. This version that I'm about to write is called the global edge version. And when we see other versions, you will start seeing why I'm giving them different names, right? So what Menger's theorem says is that the graph is k edge connected if and only if the condition we discussed is true. The graph is k edge connected if and only if there exists k pairwise edge disjoint ST paths for any two distinct vertices S and T. Okay, and we will prove this theorem, and we will do that using max flow min cut, which we will be discussing in the next 1 or 2 lectures. So, well, either we will prove it or you will prove it on the assignment, whatever, doesn't matter. We will see a proof. via max flow min cut theorem. But what I want to discuss right now is that this Menger's theorem gives you a succinct NP certificate for convincing someone that a graph is k-edge connected. Right? What you do is for every pair of vertices, n choose 2. Remember, this was not n choose k anymore. For any two vertices s and t, so n choose 2 possibilities, what I will do is I will give the person k edge disjoint paths from s to t. Right? So that means I have k paths, so it is n choose 2 times k paths, and each path has at most how many edges? M edges. And that will be a certificate for k-edge connectivity. Right? So this gives you a succinct, much better than the one we discussed before, NP certificate for k-edge connectivity. Right? What you do is, for each pair, n choose 2. For each pair of vertices, you give the person k paths, edge disjoint, right? And each path is how big? Well, it is the maximum the number of edges, right? And so you now have something that is roughly order n to the power 4 times k. Right? This is much better than our previous certificate, which was, compare this with order m to the power k minus 1 times order m, right? Something like this, right? You have spanning tree for each, yeah, anyways, I'm not being super precise here. The point is just compare the fact that this is in the exponent, here it is just a linear factor, right? Okay. So this is the power of Menger's theorem. It gives you a much easier way of convincing someone that a graph is k-edge connected. Okay. And next thing what I want to discuss, remember I call this the global version. I want to next discuss the local version. Okay. Are there any questions at this point?
Sir, just confirming. So you will be providing like the NP certificate in this case is NC2K edges.
So this is what I'm kind of looking at the how big the certificate is.
Okay, like
this is
what the certificate is like. What is the certificate then?
Right. So what is a certificate? For each pair of vertices, right? I will give you k edge disjoint paths joining those two vertices.
Okay.
That is a certificate.
Okay.
Right? Okay. So why is this a valid certificate? Well, it is a valid certificate because of Menger's theorem, right? So Menger's theorem gives you a succinct certificate for k-edge connectivity. Okay. And the different versions of Menger's theorem basically give you succinct certificates for all types of connectivity: edge connectivity, vertex connectivity, directed graphs connectivity, which we'll be discussing. Actually, no. We won't be discussing directed graphs connectivity. But anyways, if you want, you can also get Menger's theorem for directed graph connectivity. Okay. All right. So now I want to discuss the local edge version. For that, I need the notion of ST cuts. But before that, let me just talk about cuts in a graph. Okay, and I think I have briefly mentioned what a cut is when I wanted some notation, but today we are going to write down more formally. So supposing you have any graph G, okay, what you do is you partition the vertex set into two parts. So this is X and this is X complement. X is a subset of the vertices and X complement is exactly the complement set. Okay. And now you look at all edges going from one side to the other side. Okay. This set is going to be called partial of X. In many books, instead of partial, it might be what you are used to actually in some courses. They use delta. But I'm used to partial, so I'm going to stick to partial. Okay. All right. So this is called the cut, is a cut of a graph. Is the cut corresponding to set X. Right? And any such edge set is a cut of the graph. Any such edge set is a cut of the graph G. So, right? So if I give you any set of edges F, such that F can be written as partial of X for some subset of the vertices, then such a set of edges is called a cut of the graph. I want to do some quick examples. Supposing this is my graph G, is this a cut of the graph?
Yes, sir.
Okay, and what is the X?
1, 2, 3.
Right. So you can choose X to be 1, 2, 3. And now the set of edges I have shown you is partial X. And so that is a cut. Okay, another question on the same graph. What about this green set of edges? Is it a cut of the graph? Is the green colored set of edges, is it a cut of the graph?
No.
No. Why is it no?
Because we get that 1 and 2 must be in different side of the partition, 2 and 3 and 3 and 1, but that's never possible.
Right. Because if you want this to be a cut, then 1 and 2 have to be on different sides. Thank you. And now 2 and 3 have to be on different sides. And now you have a problem because 1 and 3 also need to be on different sides. Right? So this is not a cut of the graph. Okay. So the right way to think of a cut is actually you take a partition of the vertex set and then you look at all the edges going from one part to the other part. So it is a set of edges that arises from a partition of the vertex set. Okay. A cut is a set of edges that arises from a partition, but not just any partition, from a bipartition. You break it into two parts of the vertex set. Okay? Good. And now there is one more concept I want to introduce, which is an ST cut. Okay? So an ST cut is simply a cut where S is on one side and T is on the other side. Right? So it looks like this. I take a set X, and X should contain S, but it should not contain T. And so T has to be in the complement. And now look at all the edges going between X and X bar. Right? So a cut C equal to partial of X is an ST cut if S belongs to X and T belongs to X bar, or of course vice versa. S could be in X bar and T could be in X. Okay? Good. All right. So what I want to discuss next, we are almost at the end of the lecture, so I'll just tell you what's coming up next. In Menger's theorem, we are talking about K edge disjoint paths between S and T, right? But we are talking about all such pairs. We were looking at the global version, which talks about all such pairs. Next, I want to focus on just two fixed vertices, S and T. Okay? So the question is, well, maybe just let me just write a decision problem. The decision problem I want to discuss next is, given a graph G with distinguished vertices S and T, so this is a new notation, decide whether G has K pairwise edge disjoint ST paths, right? And the new notation G S comma T is simply a graph G with two distinct specified vertices. They're already given to you. S, I will call S the source, and T, I will call it the target. Okay? So this is where we will start tomorrow. And we will see a local version, a local edge version of Menger's theorem. Right? And we won't prove that either. And we will prove that using max flow min cut. So after that, we will move on to max flow min cut. Okay? Are there any questions? So please stay back if there are any questions. The lecture is officially over.
Thank you, sir.
Thank you. You're welcome.
Thank you, sir.
Thanks.
Hello, sir.
Yes. Yes.
Sir, so for the proposition like there exist pairwise edge disjoint ST paths,
Right.
for proving that it is not KH connected,
Yes.
I want to like say it like, can you tell me whether it is right or not?
Yes.
Suppose if they are K disjoint ST paths, so
Okay.
for each path, if I label every edge in the path with some number,
Okay.
so there will be k indices for denoting the edges.
Right.
So for proving that it is not kh connected, if
Hmm.
suppose I show it by, if I remove any k minus one edges, if it is still
Hmm.
connected,
Hmm.
then it then it is it is not kh connected. So
Yeah.
they are k labels, and I can remove k minus one.
Okay.
Then definitely one label. Then no edge from a label won't be removed, right?
Right. So let's go through it again because I'm a little confused. So what are we trying to prove? We are trying to prove the easy direction of Menger's theorem, right?
Yes.
Okay. So if there exists k pairwise edge disjoint paths, then G is k edge connected. Is that what we are trying to prove?
Yes.
Okay. So how do we go about it?
Uh, so as there k edge disjoint path, I want
Right.
to label each edge in a path with some number 1 to k.
I see. I have one question though.
Yes.
The so you're fixing a S and T.
Uh, for any SNT.
Okay. So between any S and T, we know that there are k edge disjoint paths. So should I call them P1 to Pk?
Okay. Sir.
Okay. Okay.
So, uh, So the from P1 to Pk, in P1 if all the edges I will label with some number 1, so till
Hmm.
in Pk it I will label edges with k. So
Okay.
uh, I need to prove that if on removing k minus 1 any k minus 1 edges,
I see.
it should be kh connected.
I see. Okay. I understand.
So I in the k labels, if I try to remove k minus 1,
Right.
then definitely one label will be there
Right.
in which no edge will be removed.
Right. So at least
So
one path will be there joining S and T.
yes,
Right. And now
so
how do you complete the proof?
even on removing the at most k minus one edges, it is connected. So h my s so this is kh connected.
I see, I see. So you're right. So basically, what you are doing is you are saying that for all s comma t, g in g minus f, s and t are connected.
Yes,
And this, since this is true for all pairs of vertices, it basically means that the graph itself is connected.
yes,
Is that right?
yes.
Yeah. So that is a correct proof. Yeah. Yeah. Thanks.
Okay, sir. Thank
Thanks,
you.
Pawan. Anthony, any questions? Anthony? Okay.